everybody, and welcome to the CERIAS Security Seminar here at Purdue University. Today is my great pleasure to introduce to you Marina Blanton. Marina is one of our best students, so I'm really happy to have her today in the seminar. And she's going to present one of her recent papers in CCS last year. It's called Dynamic and Efficient Key Management for Access Hierarchies. Marina.
Thank you. Good afternoon, everyone. And as Christina mentioned, I'm going to talk today about key management in access hierarchies. And this is a joint work with Mike Atala and Keith Frickin, all from Purdue. And as she said, the core of this work, the core of what I'm going to talk about appeared at CCS, and now I have some extensions. So the outline is very basic, it's very standard. I'm going to introduce the problem first, then describe our base scheme, provide some extensions to it. They talk about slightly different models and efficiency improvements, and then conclude this talk. So here, the basic scheme, the basic model that we're considering is there's a hierarchy of partially ordered classes. And those classes can be viewed as user classes. And those you who are not really familiar with graph theory, you might not necessarily know what partially ordered classes mean, but it is just you can look at it as a hierarchy of classes. So what we have that user classes are organized in a hierarchy, and we can model this as a directed graph. And each node in this graph is going to correspond to a class of users. And so for each node in the graph, we have a number of objects associated with this class. But it's not that everyone at a certain access class gets access to those objects. But if I belong to a certain class, I get access to objects at that particular class and everything below in the hierarchy. All objects that are stored are descending classes in that hierarchy. So this is the basic model that we're going to work with. And this is some example of a hierarchy. In the graph that you see on the screen, there are square boxes are classes, and you see there are 7 of them. And circles are objects, and they're a disjoint set of objects, and it could be 0 or more objects at a particular class. And the edges in the graph will show a relationship between different classes. And so as you can see on the picture, for example, someone who belongs to class C2 will have access only to 2 classes at that level. Someone who belongs to class C1 will be able to have access to every single object. So this is the privileges are inherited. Like every class inherits privileges of the descending classes in the hierarchy. And so you might ask, why would we care about such graphs and such hierarchies of users? But actually, hierarchies are pretty wide, used in many completely different domains. In one of the probably well-known and very heavily studied domains where we have hierarchies are back models. And in such models, users are naturally organized. They're modeled as roles, which are naturally organized into a hierarchy. And as you might know, for example, if this is for a hospital, then doctor will have privileges the same as the nurse has, and in addition to that, will have additional extra privileges. This is also useful in the context of pay TV, like cable TV and content distribution, where, for example, there could be different packages, subscription packages. So, for example, I can subscribe to a silver package, or if I subscribe to gold, I get everything that silver can offer, plus additional programs to that. Another example of where such hierarchies are useful is project development, because when there are different views during project development, for example, if a developer, I get to see just my part, all the objects and every flow that is associated with my work. But if I'm a manager, I want to be able to get access to everything that my developers work on. And so this is just the model, how this hierarchy works. But what we want to do in our case, it's not that I go when I want to access certain object. I'm not going to go and ask to authorize me based on that, based on my credentials. But instead, everything is already available. All objects are already available somewhere, but they're all encrypted. And so this problem is then that I received a key or a set of keys that will allow me to get access only to those objects which I'm entitled to see. And this is not, interactive authentication. It's basically I'm on my own, I already own my credentials, and I'm able to derive everything all keys that I need to derive to encrypt those objects that I'm entitled to see. And so this is called, and this we call this is independent key derivation because it doesn't, you don't need any third party or any server to be able to enforce these policies. And this is similar. It doesn't imply, any sort of interaction or online system. It can be even your local storage when you get a CD that encrypts certain files or movies or whatever documents that you might want to have, and then your user obtains keys that will allow to decrypt only those objects that were included in the subscription. And so how this system, key assignment management systems work, usually we get a number of things, how to evaluate them, to make sure that our scheme is efficient and is going to provide good performance. And now here I list a number of criteria how to evaluate such a system. So the first one is a number of keys per access class, and those are secret keys. So it's going to be private storage for a user. And it's obvious that you don't want every user to store a huge amount of data. And in many cases, the client can be very weak, like a smart card. And then in that case, you want to minimize the amount of storage that every user has. And then the second one is server storage space, which is public information associated with the hierarchy. And so why we need this information, in certain schemes, this will allow us to provide a more efficient performance if we store some additional information that is associated with a graph. For example, if we store just the data structure, the graph of access classes, this might be very helpful to people who want to derive their keys. And next property is low key derivation time, meaning that if I belong to a certain class and I want to get access to a different class in the hierarchy, I shouldn't have to spend a lot of time trying to get the key to my decryption key so that I can get access to the object. So this is one of the performance criteria that also look at. And next property is collision resilience of the scheme. And what I mean by collision resilience is, for example, I have access to a certain class, and my friend has access to a different class, and it should not be possible for us to combine our keys in such a way so that we get access to something else that we couldn't get individually. So it should be resilient against collisions of number of parties, or even if I get two different keys on my own, I shouldn't be able to get access to anything else that what I'm already can access legitimately. Um, and the last property that we want to have in such a scheme is that all changes to hierarchy are locally contained in the graph. And what I mean by this is throughout the operation of the system, when after it's deployed, there will be changes to the hierarchy. When we want to add a user class or want to restructure or maybe do something else that we need to do. And if just one portion of the graph changes, you don't want to affect everyone in the system. You don't want to have to go, oh, I'm sorry, we have to change all secret keys right now because we need to introduce some changes. And so it's important that all changes in the graph are locally contained. They don't propagate, they don't affect everyone else. And so the question here is how many keys do we have to have per user class to be able to implement, to be able to do all of these properties. So when we just started working on this problem, we considered different graphs with different structure, different properties. And say, for example, for a tree, it's obvious that a tree can be represented by it can be totally represented by this pre-order and post-order. All nodes for trees, two keys are going to be enough in any case. But later on, if you look at more complicated graphs, it's not really clear how many keys you need to have. Um, but then it occurred to us that if you just with just a little bit of public information, you'll be able to do this with just a single key. And it's like, wow, this is just such great result. I mean, it looks like you need only one key to be able to do anything for any arbitrary graph. In actually our scheme, it works for any type of graph, even for graphs that have cycles. And it's not that such graphs with cycles are useful in any real life application, but it's not the scheme is not limited to any particular structure. Um, in um, in here, this is in a nutshell the properties that we have. As already said, we have just one key per access class. The public storage space is optimal. And what we mean by this is that you still have to store the access graph, the access hierarchy, but we also store our public information. It's asymptotically the same as information needed to store the graph. So it's just a small constant that we introduce. All key derivation is based only on hash functions. So this is very fast. There is no expensive cryptography, just hash functions. And all changes are locally contained. Uh, and security is we have provable security against collisions, and we show that any adversary who can corrupt any number of nodes in the graph won't be able to achieve anything else that those corrupted users can already achieve. In previous results had some of this property, but it was the first one to combine all of this together, to have all of them at the same time. So this is a little bit, more specific program description, and here you can see that we model this graph. This is a directed access graph, which we call G. And all nodes that correspond to user classes are numbered as V1 through Vn. So there are going to be n classes in the hierarchy. And each node has a set of objects associated with this class, and there are all disjoint sets. And edges are inserted into this data structure according to the relationship between those classes. And we'll just call those edges E1 through EM. And since we need these properties so that everyone at a certain class should be able to have access to descendant classes. So if we have an edge from node Vi to Vj, that even if I'm at the parent node, I will be able to derive a key at the child node. So this is just one link. But if there is a longer path in the hierarchy, and if there is a path from node Vi to Vj, I will be able to have access to that node Vj. So you gotta follow this path to get access to the node that I need to access. And so that we say that a key allocation implements a particular access graph J G, if it assigns keys to both users and objects in such a way that a user can access object if and only if that user has a key, decryption key for that object. And so now I would like to talk about the scheme itself. Here it consists of several parts, one of which is key generation. And to generate the key, we need two major pieces. The one piece is private information that is going to be stored on the user side, and another piece is public information that is going to be publicly stored at the server. Um, and private user key, secret key, will be chosen at random for each class. And as you can see here, suppose I belong to a node vi. Then for that particular node, we at random pick a key and call it ki, and it's just a random string of a certain length. In this case, it's going to be raw, which is a security parameter. And so if I'm entitled to access to a certain class, that I'll get a secret key for that particular class. And if I'm entitled to get access to more than one class, um, separate class, that I'll get a key for each of the classes to which I belong. And this is not, here we're not talking about descending classes. Here we're talking about completely, different access classes in the hierarchy. For example, I can subscribe to sports, to a sport package, and I can subscribe to movies. And as my sport package will contain basketball and football, and I get access to all of those. And at the same time, I'll get a key to access all movies. And public information associated with this graph um, consists of public labels for each node. And a label for node vi will be called li. So it's just also a string that uniquely identifies a, just some label associated with this. And another piece of information publicly stored on the server um, is uh, one string for each edge. This is kind of hard to visualize this or understand just looking at this expression. But actually, what you need to understand from this is that for each edge, we store some piece of information that depends on both depends on the parent and the child keys for that edge. And so using that information, everyone who belongs to the parent node will be able to derive the key for the child node. And as you can see here, h is a hash function, and this information, the public label stored at the server, is a function of both keys of the parent and child, and the child's label. So now we need to see how we derive keys at different levels. So for instance here, suppose that vi is a parent or vj. And so using public information, we can derive the parents the child's key, and this expression is not very difficult. So as you can see, all you need to do, you take your own key, produce a hash, and take your own key and a label of your parent, produce a hash, and use public information to derive the key of the child. And so this is just one link to go from a parent to a child. But if you want to traverse the graph using several hops, you just repeat this procedure with the key that you just derived. So you'll jump from one node to another until you reach the point where your object is, where you want to access it. So it's kind of recursive procedure. Um, and security properties of this scheme allow you, it's the first one that it's sound, which means that if I'm entitled to see something, I'll definitely will be able to get access to that. And the second one is completeness, meaning that if I'm not entitled to see something, I won't be able to do that. And even it's probably secure even when someone can adaptively corrupt different nodes, different users, and so that we still show that it's impossible for them to get any additional information using any number of keys, any combination of them. So this is some example, a simple example how it works. And this graph is a little bit more complicated than a tree because you see there's edges coming to the same node. And here, if for example, say I'm at node 3, that I will be able to derive a key for node 4 using public information. And if I'm in node 1, I'll be able to get access to everything in the hierarchy. And on this graph, it's not clear, but all keys, K1 through K4, are private, but everything else is public. So you'll be able to use that information, the labels, and the information about the edges to derive keys of other nodes. So now I'd like to switch to the dynamic version of this scheme. And as already mentioned before, that throughout their operation, hierarchies are going to evolve. So there can be a number of changes that happen to them. In, for instance, addition or deletion of classes when we want to restructure the hierarchy, or we want to add new relationship between classes, add new edges, or remove some other edges, or if we simply just want to rekey a certain class because we know that the secret key for that particular class was leaked. The previous scheme is not going to support this very well, but if we just introduce small changes to the basic scheme, then we'll be able to support all of the required changes. And here, the only change that we need to introduce is to the private key. And this is pretty small change. It doesn't make it much more complicated. So as before, for each node, we pick just one secret key. But this time, and it's picked at random. But this time, instead of calling this K, we'll call it K hat. And as before, this is going to be the secret key for each user. And if you want to have access to a certain node, you get that key hat that belongs to that particular node. But now, actually, the encryption key used in the hierarchy is different. It is derived from the secret key and from the label. So this is one additional step that we insert in between using one-way hash functions. We'll see how this will help us to make sure that all dynamic changes are locally contained in the graph. And the rest of the scheme remains unchanged. And next, I would like to show how changes are introduced in the graph. An insertion of an edge is easy. So everything you need to do is basically create a public label for that edge, and we're done. This will allow us to go from one node to follow that edge, basically derive necessary keys. But deletion of an edge is trickier. And first of all, we can just take that edge out. It's not a big deal. But the problem is, if someone stored that particular information, they still will be able to have access to the node, even though right now they're not supposed to have access to it anymore. So we need to do something else. And this is called X-member problem, when we want to make sure that people who used to have access to something don't have access to that anymore. And the description of what actually needs to be done maybe not very clear here, but the basic idea is that what you need to do, you take all children of the node affected and you change their labels. So this is public information only. Secret keys are not affected. And you regenerate all public information that is computed based on those new labels. And in this case, since the public information changed and the keys changed, and in this case, people who used to have access And if they're not able to derive it right now, they won't have access. So the X member problem is solved. Um, the next thing that we need to look at is insertion of a node. And actually, insertion of a node or deletion of a node are easy given that we have basic operations for insertion or deletion of an edge. And so to insert a node, you basically create a new node and insert necessary edges that touch that node. And to delete a node, you first remove all edges that touch it one at a time, and then take the node out. So it's also pretty straightforward. And then the one last operation that we want to be able to do is key replacement. As already said, if we know that the key was compromised, we want to replace the key and rekey all users that belong to that particular class. And so to be able to do this, what we do, we create a new secret key. It's going to be a new random number. And then we compute the encryption key for that class, which is going to be hash function of the secret key and the label associated with that class. And since this key modified, we also update public information about incoming and outgoing edges for that node because they're a function of the secret key. And so with this, we actually locally contain those changes. We update only one node and edges, public information about the edges that touch it. And the difference here with key replacement, we change the secret key. But with the deletions, we actually change the labels. The secret key remains the same, and so the users are not affected. Their key stored on their end is not affected. And this is actually the novel part that hasn't been done before. And I would like to spend a couple of minutes talking about other models, other access models. So in this basic scheme, which is very natural, very straightforward, when you have access to everyone below you in the hierarchy, there might be situations when you need actually to enforce policy that works the other way around, so that I'm able to access something higher up in the hierarchy. For example, I'm a student at Purdue, and I'm entitled to see all documents stored at the level of the department. And then for me to be able to go up, there should be some sort of mechanism, like we need to reverse the mechanism that we use to be able to support this. Um, and so this kind of inheritance is called downward inheritance. And to be able to do this with our scheme, the main thing that we need to do is to generate a reverse of the graph, of the access graph that originally have. And so in the reverse graph, which we call GR, we reverse all edges. Basically, if there was an edge coming from a node A to node B in the original graph, we replace it with an edge going from node B to node A in the new graph. And then we run the same key assignment scheme. Everything remains the same, but right now it works the other way. And if you wanted to support both, then you'll have one key for the normal graph and another key for the reverse graph, and then you can have both policies in place, and they're actually the set of objects. You might be able to access certain objects using one policy and different objects using different policy. Another variation of the basic model is limited depth inheritance, and as the name suggests, that you will be able to get access to objects only above you up to a certain depth or below you up to a certain depth. There's a limitation, how many levels you can go. And to be able to support this policy, we also need to do a little bit more work for this graph. And so the first thing, we assume that the access graph is layered. And many graphs are not, but it's not very difficult to modify one by adding additional nodes to make sure that this condition is true. And so what layered means that, intuitively there are layers, right? And we modify or we partition all nodes in the hierarchy into disjoint sets. And for example, we say if for each edge in the hierarchy, if there is an edge going from node A to node B, and if node A belongs to a certain level, then node B is going to belong to the next level. Um, and then having this information, having those layers, we create we create an access graph where there is just one node per layer, and we kind of link them together. We create an edge. We create an edge going one way, and we create edges going the other way. And so in this case, if we have a key that can be derived one way and key that can be derived different way, you kind of for each user you give one starting point and another starting point, and everything in between can be derived for that user. But unfortunately, with this approach, the scheme is not collision resilient. It means that if I have certain privileges, someone else has different privileges. We are able to combine those keys in such a way so that it's possible for us to get more information that each of us can get individually. And so this is, kind of future work to, to have a scheme that will work in inclusion resilient manner uh, for this particular model for limited depth inheritance. But if you consider, all of these different access models, they'll actually be very powerful, and the policies that you can uh, uh, support will be rather rich. And it's not just going one way or the other way. You can support a very um, rich set of policies for access hierarchies. And now I'm gonna switch to a little bit more algorithmic part of this talk, which deals with efficiency improvements. And so, as I said earlier, in this hierarchy, to be able to derive a key from one node to a different node, you have to traverse every node on the path. And in some cases, that particular graph can be long and skinny, so the depth of it can be pretty long. And it doesn't happen in many applications. For example, on average, if these are rows in our bad model, then you have only usually have constant number of levels, uh, constant depth in this graph, how deep you want to go. But in certain other applications such as manufacturing, when you have a lot of different components that have to interact with one another, and then this graph can become pretty large and pretty deep. And so in this case, in the worst case, the work that someone needs to do to derive a key to a certain object will be linear in the size of the graph. And for balanced trees, for example, it's going to be logarithmic, but in worst case scenario, it will be linear. And so to be able to avoid this, to be able to make this key derivation time shorter, we use a technique so-called shortcut technique, that we add additional edges that still preserve the structure of the graph, they still preserve all relationship, but they will allow people to perform key derivation much faster because of those additional edges. And for now, let's assume that we're working with a tree of n nodes. And we have two different results actually. The first one is that if you add only a linear number of nodes, a linear number of edges to the graph, then key derivation time will be guaranteed in log n steps. And this is double exponentially better than the linear time that we started with. And if we in here number of the edges introduced is asymptotically the same as number of nodes, so it's just a constant increase in space. But if you allow just a little bit more space to be used for the graph, and if we add n log n edges, that every node within this graph becomes reachable within 3 hops. Um, so it's not a very large increase, but key derivation time is going to be much faster. It's going to be 3 hash functions, which is very fast. So these are some ideas how we do this, and I'm not going to go into very details um, because it becomes somewhat complicated. But I just want to give you an idea of what techniques we use. And the first definition that I'd like uh, to remind is that uh, we're working with a tree is that there's a notion of centroid, and a centroid is a node which, if you remove that node from the tree, it leaves no connected components of the tree that are larger than half of the original tree. So we kind of take one node, and all parts that remain will be twice as small as the original tree. And so the basic idea here is that we pick a particular node in the graph, and we're just gonna look at subtree rooted at that node. And so the first thing that we do, we compute a centroid. So we know that partitions it into that actually partitions it into pieces that are at least half of the size. And then we take that node from that subtree and start the procedure again on the remaining. So we kind of make it smaller and smaller every time until it becomes empty. And this is just recursive procedure for a node, but it's used as a building block in the larger algorithm that I have. And so if you execute this basic procedure for every node in the graph, the number of edges that we add is n log n, and additional edges or any distance between any two nodes will be guaranteed logarithmic time. And so this is not the results that I promised earlier, but this is just the first step towards the goal. And other techniques that are used in these efficiency improvements are so-called centroid decomposition. And the way centroid decomposition works is that you take original tree and you compute a centroid and take it out. So you have remaining parts that are much smaller than the original tree, and then you recursively repeat this procedure, compute centroids of the smaller trees, and remove them until the size of every tree remains 1, and until we actually partition everything completely into separate nodes. And then you basically you record the sequence of those centroids that were used in that centroid decomposition. So this is not new, and it's very standard in um, in people who work in algorithms area. But what we use here is not regular centroid decomposition, but so-called prematurely terminated. That and so the idea is still the same, that you compute a centroid, remove it, then compute centroids of the remaining parts and remove it, but then we stop not when it's become of size 1, but we stop much earlier. So we stop prematurely when with the small trees of a certain size. In our case, it's going to be logarithmic in the size of the original tree. And so the basic idea here at a high level, so those centroids that we have so far, they're going to be special nodes, and they're all together. They're all very well connected, so they're all connected with each other. And the other small parts that are remaining, we used our basic procedure on them, and they're sort of connected. Those special nodes are served as a beltway between those little small trees. And so if you want to go from one part in the graph to a different part, you use those special nodes as a beltway. You first find a centroid of your small tree, and then from your special node, go to a special node of the target tree and find your way to the target node. So they kind of provide a fast connection to the part of the tree that you're interested in. And this technique, using these techniques, allow us to both have a better key derivation time and reduce the number of edges that we add to the graph. Um, yeah. And as I said, this is not going to be necessary for every particular graph, but in cases when you want to make sure that the key derivation time is fast, you apply these techniques. And this is all I wanted to say about efficiency improvements. And now I'll talk for 2 minutes about extensions that we have to this work. And as I said before, we have a security proof of the main scheme, but it's not the strongest security model possible. And yes, I said it works against an active adversary who can corrupt as many nodes in the graph as necessary, but that adversary will be able to distinguish a key um, from a random number. For example, if I see my parents' key, then if I combine that with the public information that is available out there, that I'll be able to tell whether it's real key or not, and this is not desirable in many cases. And so instead, we can achieve security, uh, and well, we can show that the scheme is secure under key indistinguishability if we would just modify it slightly. And so the key idea here is instead of using the same key uh, in the public information in encryption, we separate them. We split this key into two different parts, and one is going to be available in the on the is a public information, and other will be used for encryption. I still get just one single key, but I'll be able to generate both encryption key and key used in the public information. But to other people, those two keys look completely random. They're not related in any way if they don't know where it came from. So this is one extension. Another extension deals with efficiency improvements. And as I said earlier, those techniques that we had work only for trees. They're not just for trees, but for hierarchies of similar structure. Of the property that they need to have is that they can be recursively decomposed in smaller parts. And there are some other graphs that have the same property, but not a lot of them. And of course, we want this to work for general structure for general access graph. And it turns out that if we use the notion of the dimension of a graph and combine with this technique as a building block, you actually will be able to achieve um, much faster key derivation time compared to the original scheme. And this is all I had for this topic, and just want to conclude. I want to summarize the properties of the scheme and just briefly mention future directions. And so, as I said, we have a scheme for key assignment which has just one key per user class, and then allows the user to derive access to all objects below in the hierarchy using fast hash-based key derivation. And the scheme is resilient against collisions, it's probably secure. All updates to the hierarchy are local, are handled locally. They do not affect any other part of the graph, and the key derivation is bound by the depth of the graph, but can be significantly improved if you use efficiency improvements techniques. And one of the future directions that someone might consider is temporal constraints and or so-called time-based access control. And it's important in many cases, especially in RBAC models, when you have someone who is entitled to have access to certain things during their work business hours, but after a certain hour, they shouldn't have access to those things anymore. Or people who work in shifts, or even subscriptions. For example, like if I have subscription to access something on weekends or evenings, there are still all of them are going to be based on the time of access. And the last thing is support for collusion resilience and limited depth, permission inheritance that we didn't achieve in the current scheme. And this is all I wanted to say today. And if you have any questions or any comments, I'll be happy to answer.
Is the last point there, does that handle a case where you had one graph where the bottom node was connected to two higher nodes? Does this handle that case where you have limited permission inheritance and maybe you have two nodes on the path on one side and only one node, so the level is different depending on which path you take?
Yeah. So you first, to be able to support this, you first want to make sure that it's layered. So if the number of nodes on one side is larger than the number of nodes on a different side, you just insert a fake node to make sure that the level stays the same.
So if you're on the key assignments running downward and upward, then is every node going to have access to every other node, or only to their own parents, only to their own ancestors?
No, it's going to be only to their own parents or ancestors. And as I said, the set of objects can be disjoint, right? So things that you can access going down may be different from the things that someone can access going up. But it's still, yes, I will be able to have access only to my parent and their ancestors if I'm going up. If I'm going down, they're going to be just my descendants. Do you have a question?
It's listed like future directions, but like for the temporal constraints, do you think you can achieve something without re-encrypting every time? And also, how do you? I mean, I don't know how much you've been there, but like, do you think there's a way to prevent if someone archives the data to use that archive later?
I don't think you can avoid re-encrypting. With this model in place, if you change the key, everything is already there. Everything is stored, encrypted, and then you'll have to encrypt everything with a new key. Yeah, this is. With this particular model, you probably don't want to have really fine granularity because you have to, encrypt your database, everything, and this particular work is concerned just with having, proper access. So um, you know, if someone stores the content of a file, we can't do anything about it, and it's the case in many other models. But the key thing here is that it's much more easier to store just the key than to store a huge file or a movie.